And we're ready for the fifth and final podcast of this week. Single replacement and double replacement reactions, both familiar to you, both gone over in Science 10. Now, ultimately, in single replacement reactions, guys, there is a key thing that often gets forgotten. Now, it is not the fact that we have a switching of one element for another. Now, let's either the cations will switch places or an anion will switch place. Fine, that's fine. Here's the key thing that's forgotten. They will involve an aqueous ionic compound reacting with a single element. In other words, this reactant is going to be aqueous. It will not necessarily tell you that in a question. You need to know that. Now, this product as an ionic compound is something that you're going to have to check the solubility on. Water is going to be present. Will this thing be a precipitate? Will it be aqueous? You need to figure it out. So hint, do not lose sight of that. Now, with a single replacement reaction, there are those two different options of how this could go. Either it's a circumstance where A and B, in this case, are going to switch spots, or potentially you're going to have those anions switching spots instead. How do you know what's going to happen? Well, you got to pay attention. A metal will swap places with a metal, and an anion or a negative one will swap places with what else could be an anion. Okay? Pay attention, be aware of what's happening. Notice though, right, when copper is here, this is a metal atom. This silver that's in the compound, this is a silver ion, right? That's very different. And when it gets kicked out by itself, it is no longer a silver ion. It has now become silver metal. Huge difference. And this is why it's a reaction. Things have changed. And copper is no longer copper atom. It is now a copper ion over here. So when these get kicked out, they don't remain ions. They go to the element form. They become atoms. Definite, distinctive difference. It is, however, the two that have potential to be cations that are the ones swapping. Let's check out an example here. So first example, always watch the wording. We need a balanced chemical reaction. It doesn't tell you the type. It doesn't say formation, decomposition, combustion. All you know is you have a metal zinc and you have this. Oh, that's not an ionic compound. However, you know that ions are present with it. Hydrochloric acid is one of those formulas you need to know. What is it? Well, it's HCl. And we know that acids, no exception, are always aqueous. Now stop and think about this. The zinc is a zinc atom. But when it turns into an ion, it becomes positive. Which one of these is positive? The hydrogen or the chlorine? Oh, it's the chlorine. That means that it's going to be these two that will switch out places. Okay? So when the hydrogen gets kicked out, it's no longer a hydrogen cation, it becomes an element. And hydrogen is diatomic as an element, so it'll be H2 gas. Plus, the zinc will now become its common ion, which is zinc 2 plus. So if you need to, you might have to write these out to figure it out. It'll be zinc 2 plus. The chloride ion is still there. Drop and swap. We will get zinc chloride. Okay, and there'll be two of them. Check your table. Come over here to this thing. Have a look at it. Be like, okay, we're dealing with chloride. Where does zinc fall into it? Zinc is not copper 1 plus, silver, the mercury diatomic ion, lead, tellurium. No, zinc is going to be in most, which means it is going to be aqueous. Most common mistake with these is you got all that prediction done and whew, life's good, and then you forget to balance. Don't. You have to balance them still. They're easier to balance than combustion, but always do it. We have 2 hydrogens produced, so we need 2 to react, which works out perfectly because there were 2 chlorines produced, 2 are now reacting. Easy, done and done. Usually single replacement reactions are fairly easy to balance. Moving into example 2, balanced as usual. Reaction, what kind? Well, let's investigate. Aluminum chloride, we have an ionic compound with bromine, single element. That's key. An ionic compound and bromine, this is definitely single replacement. So aluminum chloride, you're going to have an aluminum 3 plus ion mixed with a chloride ion. Drop and swap, that'll be aluminum Cl3. Remember what I said, you always assume that the ionic compound in a single replacement reaction, that's the exception, is aqueous. Plus, it's mixing with bromine. Bromine is diatomic, Br2. Check your periodic table. It is a liquid at room temperature. Now, what's going to swap this time? Well, bromine is a non-metal, guys. It becomes an anion. So the only thing it could possibly swap out with then is the chlorine, because that is also an anion. When it kicks out the chlorine and goes in with the aluminum, it becomes the Br negative charge. So let's put those together. It'll then be Al3 plus mixed with Br negative. Drop and swap. You'll have Al Br3. Is it aqueous or not? Don't guess. Be positive. The bromine is located right here, just below that chlorine. And notice that we end up with zinc once again being with most. So that means, yeah, it is aqueous. Oh, well, that's good. But don't guess. Always check. The chlorine, on the other hand, gets kicked out. It's now an element. It's not an ion. Elemental chlorine is diatomic, Cl2 gas. Let's finish by balancing this thing. We have 3 chlorines going in, 2 going out. Not going to work. We got to get them to an even lowest number. So 6 going in and times this by 3. 6 going out. Bromine has the same issue. So times this one by 3. This one by 2. Done and done. And we made sure, like I said, to check the solubility of that ionic compound that was formed. There you have it, guys. Single replacement, done and done. Double replacement, in perfect honesty, I think is even easier because you're guaranteed that you can always just swap out the same thing. Swap out the cations, the positive charges, and you're done. The hardest thing with double replacement reactions is remembering to check the solubility of your products. You have to. Guaranteed your reactants are going to be aqueous. These reactions aren't going to happen unless these ionic compounds are dissolved in water. But the products are a whole other story. You might get a precipitate. You don't know. So we consider the ionic compounds that you're reacting to be dissolved. They're soluble. But again, I come back to that word. You end up with a product potentially that's a precipitate, an insoluble, solid ionic compound, right? You need to always use that solubility table to double check. Ultimately, though, just in terms of how these reactions work, they're not so bad at all, right? Just swap out the cations, easy peasy. You can see by the example below, sodium switches places with the copper, life's good. And when we check the solubility table, we do indeed end up with a precipitate. Okay, let's try a couple examples. Oh, sorry, first before we do that, this is also a double replacement reaction. These came up when we were talking about acids and bases. Neutralization, just a special case. It is still double replacement, guys. But the key thing with this is we now react an acid with a base, and guaranteed the products are always a salt and water. Now, a salt is just a soluble ionic compound. It doesn't mean NaCl necessarily. What I call to your attention, though, when you're dealing with neutralization, is that water is often easier to understand if we write it as HOH liquid. That way you can visually notice that you've got that hydroxide still being part of it, right? And you can visually notice that this hydrogen came together here. Yeah, check out that swapping, right? Okay, it still is. This one swapping with this one. Same. Neutralization. Okay, special type of double replacement. Here we go into a couple examples. Balanced chemical equation reaction doesn't tell you what kind, so you would have to recognize, hey, I have an ionic compound not reacting with an element by itself, but with another ionic compound. That's how you know the double replacement. 2 ionic compounds reacting together. Or in the special case of neutralization, an acid and a base reacting together. Let's check out these ions so we can predict the formulas properly. Aluminum is Al3 plus, nitrate is NO3 negative. Now going into the next one, ammonium is NH4 plus, not ammonia, ammonium. Phosphate is PO4 3 negative. Drop and swap, figure out your balanced formulas with charge. We will have aluminum bracket NO3, 3 of those. The reacting ionic compounds are always aqueous. Remember that. Plus, the next one is going to be NH4 in brackets. There's 3 of them. PO4, always aqueous. There it is. To produce, here's that switching of cations. Aluminum is a cation. Ammonia is a cation. They're going to switch places. Pay attention to what their charges were so that you can correctly predict those products. Okay, so aluminum is a 3 plus charge, phosphate is a 3 plus charge, they balance, AlPO4. We'll do the solubility afterwards, leave space for it. Plus, now we go to the ammonium and the nitrate, a positive one, a negative one, they also balance. We have NH4, NO3, leave the solubility for a moment. Go to your formula sheet and double check what those would be. We have phosphate. So our phosphate is right here. And with phosphate, the only ones that will be aqueous are with group 1 or ammonium. Well, aluminum is not in group 1. Aluminum is not ammonium. It would be under most. This is our precipitate, guys. Without a doubt, we have a solid form of that aluminum phosphate being formed. Vice versa, for the ammonium nitrate, we would do the same kind of a process. Find the nitrate. Nitrate's over here. And then we would look for where ammonium would fit. And ammonium is not rubidium, cesium, silver, the mercury one. No, it's under most. So definitely going to be aqueous, AQ. In terms of a balancing out for this, no big deal. We just have 3 ammoniums going in. So we're going to put 3 there, and that balances out the nitrates. These are also beautifully easy to balance. Much, much easier than those combustion reactions. One more example for the week, and then week 7 podcasts are finito. Balanced reaction. Check out this one, guys. Pay attention to this sort of thing. Hydrosulfuric acid and potassium hydroxide. Ding, ding, ding. We have an acid. Hydroxide is here. This is a base. Acid plus a base. It's still double replacement, but it's a special kind double replacement called neutralization. Hydrosulfuric acid, that is hydrogen with sulfur. If you forget what those are, you're going to have to go back and look at them. Acids are always aqueous, no exception. Potassium hydroxide is pretty easy. K plus charge, hydroxide OH negative, again, aqueous. We will swap out what will become positive charges. So those two are going to switch, which means potassium K plus is going to go with the sulfur 2 negative, which is our K2S. Okay? Is that going to be solid or aqueous? We'll find out in a second. Plus, last one there is water. Remember what I said. It is much easier to balance these if you write it as HOH instead of H2O. Means the same thing, but this is easier. Trust me. Water's a liquid. You don't have to predict solubility. You know it's a liquid. It's a molecular compound. Let's check out that K2S because this is kind of a weird one. Now, when you look at this, that K2S, you're not going to find sulfur 2 negative anywhere on here, but potassium, the K plus, is a group 1 ion, guys. So it's that weird situation where we look at the cation instead. And sulfur does not fit in here. It is under most, which means K2S is indeed aqueous. Neutralization, the salt forms, will always be aqueous. Let's finish this off by balancing. We are going to have 2 potassiums formed, so I need 2 reacting. That means I now have 2 hydroxides, so that's easy to balance if I put a 2 here, which my 2 hydrogens are also good. I have 4 hydrogens total reacting, 4 hydrogens total produced, done. All right, guys, you can now finish this assignment. work on 6, 7, and 8. There will be a mishmash of the different reaction types. So you're going to have to really think about how to identify one type of reaction versus another. Good luck as always.